All right, hello everyone. Welcome to the next lecture. Again, we are covering this chapter, natural and step responses of RLC circuits. In the previous lecture, we, in a lot of detail, cover about the natural response of a parallel RLC circuit, and we looked at its different responses: overdamped, underdamped, critically damped, right? And here's a summary of that natural response of a parallel RLC circuit, right? When we solve that circuit for the voltage, we ended up finding out this second order differential equations, and then we further solved it to find this characteristic equation, right? This was a quadratic equation, and this is how we can find the two roots of this quadratic equation. We also defined this values of Napier frequency, damp frequency, resonant frequency, and omega d is actually your damp frequency, right? And then we can define these, not define, we can calculate these variables, the alpha, omega naught, and omega d, and based on how these values of alpha and omega naught looks like, we get the three responses, right? For example, if alpha is greater than omega naught, then you get an overdamped response. If alpha is less than omega naught, you get an underdamped response. If they are equal, you get a critically damped response. We also saw for different responses the different equations for the voltages that we get and how to get the constant values as well. For example, in the overdamped case where alpha square is greater than omega naught square, alpha is greater than omega naught, right? We found that here is the voltage solution of a second order differential equation is going to look like, and this is how you can find the two equations as well. We kind of derive these equations, right, by looking at the voltage at zero positive and also looking at its first derivative at zero positive. And similarly, for an overdamped response, we define another equation because our roots came out to be complex conjugates, right? So our equation solution looks slightly different here, right? Then we find the two parameter constants as well. Find out these two equations to find those two constants. And then in the critically damped solution, when we solve this, we realize that we only are left with this one solution, e raised to r minus alpha t. So we had to come up with another solution and use superposition to add both of them to get two constants t1 and dt, right? And our other assumed form was t times e raised to r minus alpha t. And then we use a similar method of this, right? V at 0 and dv by dt at 0 to get these two equations. So we have gone through this entire process for a natural response, and you're going to realize that we're going to borrow in a lot of concepts and very quickly do a step response in the next 15 to 20 minutes without worrying about a lot of things, or while using a lot of things that we have learned in the past. Okay, so in this particular lecture, I am going to do the step response of a parallel RLC circuit, and we're going to do its derivation. So again, um, in case of a parallel RLC circuit, for example, look at this circuit. We have done the very similar circuit for a natural response as well. So our circuit is the same. At t is equal to 0, your switch gets open. When your switch gets open, this DC current source comes into play for the circuit. So essentially, this DC current source starts to store energy in the capacitor and inductor as well. We can, while solving for any step responses, we can always make an assumption that energy was previously stored in the capacitor and inductor, or energy was not previously stored, right? However, whenever we are solving and deriving and getting the equations, we try to be as holistic as possible. So we are going to make an assumption that energy was previously stored in the inductor and capacitor. And then, of course, if in the example problem we were given that energy was not stored in the in it before the switching event for the inductor and the capacitor, that just makes our life easier and the equations easier. Okay, for the time being, we're gonna assume that the energy was stored. Okay, generally, and then we're gonna drive the equations and find out some interesting things. One more quick thing, right? In the natural response of a parallel RLC circuit, we kind of derived these equations for the capacitor voltage. And in this step responses, we are going to realize that we are more interested in finding the equations for the inductor current, and then we can find the rest of the circuit parameters when we are going to do the rest of the example problems. Okay, so why inductor current? Because if you look at the circuit at t is equal to infinity, right? So in this step response, in this particular circuit as well, right? At time t is equal to 0, when the switch will be open, your current will start to up supply energy to the capacitor and inductor, and the capacitor will start to get charged, and the inductor will start to store energy as well. whenever that new steady state will be achieved, right, at some point in time, because the final value literally is going to come at infinity only, because of the exponents involved that we have. Okay, anyhow, once at t is equal to infinity, we know that, or at that steady state, we know that the capacitor will practically become an open circuit and inductor will practically become a short circuit. So if the inductor will become a short circuit, this is how our circuit is going to look like, right? This is your capacitor, which has become an open circuit now. And this was your inductor, which has become a short circuit now. So if the capacitor is if the inductor will become a short circuit, right? So this DC current source is practically being shorted out through an inductor. So that is why we are kind of more interested in looking at the inductor currents, or other capacitor voltages. Okay, anyhow, let's do the derivation. Okay, so what I'm going to do is I'm going to apply the KCL, and we are going to do something very similar that we did last time. So I'm not going to, right, if for example we can practically assume any node. We can see that the inductor current is leaving at this node, capacitor current is also leaving at this node, resistor current is also leaving at this node, or we can even use this: capacitor current is leaving, inductor current is leaving, resistor current is leaving, and your this current source is coming in. So your IC plus IR plus IL equals to capital I. Okay, now your resistor current IR equals to V over R. Your capacitor current equals C dV by dt. And I'm going to keep IL for now the same. Okay, so let's keep IL the same, plus resistor current is V over R, plus capacitor current is C dV by dt should be equals to the current I of the DC source. Now I'm more interested in figuring out in replacing this dV by dt, right? So I also know that in terms of the inductor, the voltage across the inductor equals di by dt, right? So I can also write this as V over L equals di by dt. I can take a time derivative on both sides, and I would get 1 over L dV by dt equals di square over dt square. Right, again, I'm only interested in replacing dV by dt, so dV by dt is L times di squared over dt square. Okay, so I'm going to replace this into this equation, and I'm going to be left with IL plus V over R plus C times L d square I over dt square equals to I. Okay, and whenever we are writing a second order differential equation, right, the double derivative usually comes without a constant. So in order to standardize this, I'm just going to divide the whole thing by LC or CL. So I'm going to be left with d square I over dt square plus okay, sorry, there's one more thing, right? Over here we have a voltage, right, and this voltage can also be replaced by LdI by dt. So let me actually rewrite this equation again. So I have IL plus V is this voltage is L over R di by dt plus LC d square I by dt square equals to I. Now divide the whole equation by LC. So you're going to get d square I by dt square plus 1 over RC. LC will be cancelled. L will be cancelled. And then plus 1 over LC IL equals to capital I over LC. So this is the equation. Let's call it equation 1. Okay. So after solving this parallel RLC circuit here, right, we got a second order differential equation because we were interested in finding the inductor current, okay, or deriving an expression for the inductor current. So while finding the expression for the inductor current, we ended up finding the second order differential equation. So what I'm going to do in order to find this inductor current, right, so all of this is IL actually. Let me clarify this in case we have missed it, okay. right, in order to find this inductor current, we have to practically solve this for the voltage. I am going to show you how. And I'm going to borrow this equation as well. All right. Right. So to solve for IL, let's find voltage V. Okay. Again, the expression that I wrote over here, IL V over R C dV by dt, I'm going to take advantage of that expression. IL V over R C dV by dt equals to capital I. Okay. I already, and again, I'm interested in finding the value of the voltage, right? So this variable is also already in volts. This is also in volts. I need to find a IL. Somehow I need to replace this IL. Okay. So let me derive this thing. Or maybe on the right hand side, I already know the inductor voltage, right? Which is V is L di by dt. So let's do this. Di by dt equals V over L. What I'm going to do is I'm going to take a integral on both sides from 0 to t, right? So integral of di by dt 0 to t dt equals integral 0 to t v dt 1 over L. Again, to avoid the confusion, this is what book does as well, and we can change the variables, right, of integration and separate them out from the variable that is used in the limits of integration. So practically we do 0 to t d tau over di over d tau dt 1 over L 0 to t, right, v of tau over d of tau. Okay, so if I were to solve this side, this is going to come out to be IL at t minus IL at 0 equals 1 over L 0 to t v times d tau, or IL of t will comes out to be IL of 0 plus 1 over L 0 to t v d tau, or since this is the initial condition, right, so I can write IL of t comes out to be I naught, initial inductor current, assuming there was an initial stored energy, plus 1 over L 0 to t v d tau. I'm going to replace this equation all the way over here. Okay, so my equation is going to come out to be very simple. IL will be replaced by 1 over L 0 to t v times d tau plus I naught plus v over R plus c dv by dt equals to I. Right? Again, I naught over here is initial inductor current. I'm going to differentiate this equation, differentiate with respect to t both sides. Okay? If I'm going to differentiate this with respect to t both sides, right, this term, your differentiation and integral will be cancelled out, so you are going to be left with v over L. Next is a constant, so it is going to come out to be 0. V over R, so you will get 1 over R dv by dt plus this term, where we're going to get a double derivative, c d square v by dt square equals to 0. Again, this will become 0 because derivative of a constant is 0. I can, again, this is a second order differential equation, and in order to write in the kind of a more standard form, I can divide the whole equation by this constant. That's right, so divide by c, I will be left with d square v by dt square, d square v by dt square plus 1 over rc dv by dt plus v over LC equals to 0. Okay, so here's the voltage that we got, the expression for the voltage that we got. D square V by dt square 1 over RC dV by dt plus V over LC equals to 0. Again, this is a second order differential equation. And interestingly, if I will just go back and show you one interesting thing, right? So this equation, which is a second order differential equation, wouldn't it look exactly same as this one that we derived in the previous expression? D squared V by dt squared 1 over RC dV by dt V over LC, right? And it had three solutions depending on what your response is. One of the solution was this in case of an overdamped response. In the other solution was this in case of an underdamped response. The third solution was this in case of a critically damped response. So we are going to assume, so if I have this equation and I have to solve this equation now, I already know the three solutions that I derived. So I'm going to write those solutions down from current. Okay. Okay. So again, solutions for v of t depends on roots of characteristic equation. That we derived in our previous lectures. I'm just going to write down all the three equations now, right? So one equation is v, which is a1 e raised to power s1t plus a2 e raised to power s2t, right? And if you remember, this was for over damped. The other is v b1 e raised to power minus alpha t cos of omega dt plus b2 e raised to power minus alpha t sine of omega dt, right? So this was for underdamped. And the third one was for critically damped, which was d1 t times e raised to power minus alpha t plus d2 e raised to power minus alpha t, right? And this was for critically damped. So these were the three solutions of this equations that we derived last time, and those three solutions would still be valid. So interestingly, what we are going to do now is we have to find, so essentially I'm more interested in finding out the answer for this equation, right, which is the second order differential equation for the current. I'm more interested in finding out the answer for the current IL, as I said, right over here, that we if at the steady state we are more interested in finding out the inductor current, and then of course with that we can find out the rest of the variables as well. Okay, so you got these three solutions. So how to find the value of L? How to find expression of IL based on this second order differential equation. So if I'm going to use this equation again, IL V over R C dV by dt equals to I, right? So IL plus V over R plus C dV by dt equals to I, right? Where again, we have this I. This I represents this constant DC source, right? And this is in the circuit for t is greater or equals to 0 or 0 positive. Okay, so how you can find out the expressions for IL is practically all you need to do is, in order to find this IL, you need to know the value of the voltage, which you already know from all these three equations, and you need to know its first derivative. If you were to replace the expressions of these V and the first derivatives into this equation, you're going to know all the values of IL, right? So for example, right, if we were to do the first one, in case of an overdamped, right? In case of an overdamped, for example, I know the value of the V. Let's find dV by dt. dV by dt is going to come out to be a1 s1 e raised to power s1t plus a2 s2 e raised to power s2t. So you can replace this thing over here plus the expression of V. So you're going to get IL equals I minus times V over R, 1 over R times a1 e raised to power s1t plus 1 over R, a2 e raised to power s2t right, minus dv by dt times c. I'm going to take c constant out, and a1 s1 e raised to power s1t plus a2 s2 e raised to power s2t, right? So if you were to solve this expression, right, essentially you're going to come out to be, and essentially I'm interested in finding out, taking out e raised to power s1t as a separate variable and e raised to power s2t as a separate variable. Okay, so once you're going to solve this, we are going to be left with capital I plus a1 dash e raised to power s1t plus a2 e raised to power s2t, right? a2 dash. And now these a1 and a2 prime constants are new constants. And again, these constants can be some combination of a1 and a2 as you are going to solve this equation. So similarly, right, so essentially what we do again is we have, let me show it in a different color to make it more easier. Okay, right. So you got these three equations for the V, three different voltage expressions, and here is your IL equation that you can potentially use. You can replace the value of these V's directly over here, and you can take the first derivative and replace it over here and solve the equations, right? And again, you're going to get another equation for overdamped, another equation for underdamped, another equation for critically damped. And again, once you're going to get all of these three equations, in case of an overdamped, you're going to get some combination of A1 and A2, some combination of B1 and B2 in underdamped, and some combination of D1 and D2 in critically damped. So once you're going to solve those combinations, essentially you're going to come up with new constants that will be some combinations of the previous constant, but we don't care eventually because our new constants, we can directly solve those constants from our circuits. Okay, so I'm going to write down the new equations. Not from start, sorry, from current. Okay, so your IL comes out to be I plus A1 prime e raised to power S1t plus A2 prime e raised to power, e raised to power S2t, right? This is an overdamped case. And similarly, I'm going to write the other equations. IL comes out to be I. This is a DC source again. And rest of the function is going to remain very similar if you actually compare. B1 dash e raised to power minus alpha t cos of omega dt plus B2 dash e raised to power minus alpha t cos of omega dt. This is for underdamped. And the third one is capital I plus d1 prime t times e raised to power minus alpha t plus d2 prime e raised to power minus alpha t, and this is for critically damped. Okay, so again, these three equations are coming from solving this equation here by replacing these three equations and replacing them for the value of V, and also doing a derivative with respect to V and plugging it back in this equation. Okay, sounds good. So these are the new equations, right? And if you look closely into all three equations, these equations looks very similar to the previous equations. The only difference, if you actually look closely, is your constants. Now you have new constants, and we can see that in all the three different cases we have two constants to solve. And again, we made this kind of a huge argument, a deal about having two constants to find a solution for a second order differential equation. And then there's like one more extra thing over here, which is this I. This is this extra DC source that is present in case of a step response. So this is all great. By the way, this method is called an indirect method. I'm going to show you another direct method, which is a much more simpler method in which we don't need to do any derivation once we find the natural response. Okay, so let's quickly talk about the direct method. So the direct method uses one of the fundamental principles of solving a differential equation with a forcing function. And that somehow that thing states that if you are in need of finding a solution for a second order differential equation, right, which has a constant forcing function, right, and the constant forcing function in this case is essentially your DC current source. That is a constant DC source that gets added at time t equals to 0 and continuously provides energy to the inductor and capacitor till some steady state is reached. So that is a constant forcing function, right? And in case of a natural response, we are essentially kicking these sources out. Okay, so the principle that we are using is in this kind of a direct approach is a solution for the second order differential equation which has a constant forcing function. In our case, let's say which has a constant DC source. This solution will be equals to that forcing function. In this case, again, your current I, whatever that is going to be the final value of it, plus whatever the form that you have for the natural response. Right? So again, your current values and your voltage values over here will be equals to the forcing functions, right? IF, which is essentially the final value of the current and the final value of the voltage, plus the same form. It is not the same expression, or it has the same form, and right, same form, and that is why its overall expression will remain the same, right? So you're still going to have e raised to the power s1t multiplied with a constant, e raised to the power s2t multiplied with a constant. This expression are exactly the same. So the form is the same, however your constants are different. So that different constants, right? So you can have a same form but with a different constant. So this is a much more direct approach where practically you are saying that you can find this solution exactly by using a forcing function, IF and VF, and plus this equations, plus using a value similar expression. The interesting thing that we are going to kind of find out over here is, and we can, this IF and the VF are the final values, right? And if we solve this again, this is at t is equal to infinity, this circuit. Your final value of the inductor current becomes I, because this is a steady state that has been reached and the inductor has become a short circuit. So your IF practically becomes I and your VF practically becomes 0, right, over here, because of a short circuit. And now we can see that if we would have not done this entire analysis, and if I look at this equation again, this is my voltage equation that I solved for the natural response, right? And here are the answers for this, right? I solved that equation, this equation, and I got these three answers. For example, this is one equation, this is the other equation, and here's the third equation. So my solution for the response is going to have the same form, the same these v of t's, plus the forcing function IF, which in this case is going to be 0. So that is why we don't get any functions. I'm going to show you in a second. And then the constants are going to be different. So that is why we have those prime constants. Let me go back, right? So if we are solving this equation, we get these three solutions. These three solutions. And in these three solutions, I have different constants. Sorry, this is... Yeah, okay, so this was for the initially for the previous equation, and once we find it out, then we got these new constants, right? So these are the new constants. Okay, sounds good. So practically again, your VF comes out to be 0, and that is why in these voltage equations, again, you did not have any constant, and we can use the similar forms. And in the current equations, we have this I as a forcing function, because IF becomes I at t is equal to infinity. Okay, great. So I'm going to show you a kind of a stepwise process very quickly on how to solve these circuits, and then in the next part of the lecture, we are practically going to do a few example problems just to make this thing more clear. And the stepwise process is very much exactly similar, not the same, similar to the natural response as well. Okay. The very first thing is you have to find the initial conditions if it is not provided in the problem. Solve the circuit for t is less than 0 and find the value of v naught and I naught. And since we are talking about the step response, so we are also interested in finding the final values. And again, at t is equal to infinity, we just saw that we are interested in finding the final value of the current. The final value of the voltage is going to be 0, right? So Vf is going to be 0. So yeah, it's okay. In the second step, again, if we have RLC values known, then we can easily find the value of omega naught and alpha. And then depending on the nature of these alpha and omega naught values, we can have these three responses. And these three responses, again, if your alpha is greater than omega naught, if your alpha is greater than omega naught, you get an overdamped response. If your alpha is less than omega naught, you get an underdamped response. And if they are similar, you get a critically damped response, right? You get an underdamped response because you get complex conjugate roots. Anyhow, right? Okay, so putting down the value of the alpha and omega naught, you can pick out which equation to use. And then, of course, if you have an underdamped response, you have another variable omega d. So you have to find the value of the omega d. And once you do that, practically now you have all of these. Now the only leftover thing is, once I found the value of the omega d, alpha, and omega naught as well, I need to figure out my constants, a1, a2 dash, b1, b2 dash, and d1, d2 dash. We did this entire exercise on how to find these constants, right? And these constants can be found by finding the value of, right? So the two constants, we need to come up with two equations, and that can be found by taking IL at 0 positive and DIL at 0 positive by dt, right? So one is equating this equation depending on whichever the response is at t is equal to 0 positive, and the other one is equating these equations by taking the first derivative and t is equal to 0 positive. Okay, so you can apply this first of this condition. Again, for example, in the overdamped response, if you were to put t is equal to 0, you are going to be left with only I, right? And then at t is equal to 0, I is going to become I naught. So that is why your IF, e raised to power s1t, e raised to power 0 is 1. So you are left with I plus a1 dash plus a2 dash is equal to I naught, right? Similarly, in cos of omega d will become 1. So and sine of omega d will become 0 at t is equal to 0. So you are left with I b1 dash, and then again this entire term is going to come out to be 1 I naught, right? Similarly, if you are going to replace t is equal to 0, this is going to become 0, and you are left with I and d2 dash, and this will be I naught. So this is your first equation in order to find the two variables, right? So for example, in case of an overdamped, you still need to find a1, a2 dash. Over here, based on this and this, you can find b1 dash, and over here d2 dash. The second equation, you need to use this principle, di 0 positive by dt. And again, if you remember, we did that by equating two equations again. One, we took the derivative of these currents at t is equal to 0 positive, and we also solved a circuit, right? In terms of solving a circuit, you can use help with this identity, which is v equals L di by dt, right? So practically, if you were to converse it, you can get this thing. V over L, take it over there, dIL at 0 positive over dt, which is v0 positive over vt, and v0 positive is v naught, right? So you get v naught over L, and v naught is again the initial condition of a capacitor, or the initial voltage that is stored in the capacitor. You can equate this v naught over L, right? So practically you are going to equate this v naught over L to dIL by dt, right, at 0 positive. And again, this is coming all the way by taking the first derivative of these equations and add 0. I'm going to show you those equations. So here are the three equations. If you're going to take the first derivative and make it 0, the equation in case of an overdamped is going to come out to be this, underdamped is going to come out to be this, and critically damped is going to come out to be this, which looks very similar to the, if you actually see, looks very similar to the natural response as well, because the difference in between this one and the natural response is these forcing functions, right? And that is why those equations are very similar. Okay, so and then you can, of course, once you find all the constant, replace them in those equations. Okay, so here is the final. If you were to have a cheat sheet, which I am still figuring it out whether to allow you or not, but this is literally what you need to know. And this is very similar to the previous table as well for the natural response. So maybe you just need one of them and not two of them, and having this intuition that the only difference in between them is practically these forcing functions and the slightly changed constant. In case of a step response, we did a very similar process. Your characteristic equations comes out to be the same. Alpha, omega naught, omega d is the same. The roots are the same as well, right? When we derived these three expressions for the inductor current, right? These forms a1 dash e raised to power s1t, a2 dash e raised to power s2t, or this is very similar. This is similar to the natural response other than these very constants d1 d2 dash and these prime constants, right? And plus you have a forcing function here. And again, this was exactly what the difference was in case of our direct approach that we talked about uh, on this slide. Let me show you the slide again, right? On this slide that we talked about, that without worrying about all the derivation that we did, right? If we can take advantage of this concept, we don't know we didn't need to do the whole derivation, right? And that concept is that if you have a forcing function, right, in a second order differential equation, and you have already evaluated a second order differential equation without the forcing function, right, you can use that natural response derivation and add a forcing function to it, right? And again, your constants are going to be different, but the forms of those equations are going to be similar. And that is why all these three forms, right? So this expression, and this expression is very similar to the natural response other than the forcing functions. So these are in addition to that. So again, if you were to solve this, find the values of alpha, omega naught, omega d, and find the S1 and S2 and omega d only for the underdamped case, of course, right? And once you do that, use these two equations, and these two equations to find those prime constants. And once you do that, put everything in these current inductor current equations to find the values. Okay, so with that, I'm going to finish this lecture, and the next lecture, we're going to solve some of the circuits. Yeah. So hopefully, if you have any questions, let me know. Again, this was a you can always start from the very basics and then solve it, right? Again, in this lecture, we started with this parallel RLC circuit and derived the equation initially for the second order differential equation for the current, but we then said that okay, in order to find this inductor current, we have to find out the voltage first. And when we derived the whole voltage expression, we saw that, okay, this came out to be very similar to the natural response. This is interesting. Nice. So we already had the solutions for the natural response. So based on this circuit equation that we got by solving the parallel RLC circuit, in case of a step response, right, we can take those derivatives and find these three equations. And these are, again, three equations for the step response. But you can do all of that and avoid all of that maybe by using this kind of concept where we kind of talked about this. A second order differential equation with if you have a constant forcing function, that equals to the forcing function plus the similar response to the natural response that you got, similar expression to the natural response that you got. Okay, so with that, I'm going to kind of finish this lecture, and in the next part of the lecture, we're going to talk about some of the example problems. All right, with that, thank you so much. Have a great rest of the day. Bye.